Welcome to Monochromators. A monochromator takes in multi-wavelength light and returns a single wavelength. Well, really, a narrow band of wavelengths. So, a simple monochromator can be made from a box and a prism. If we cut two narrow slits in the box, such that light passes through the entrance slit over here, it gets dispersed by our prism here, and then the wavelength of interest passes through our exit slit over here. Other wavelengths, because the prism bends light of short wavelengths differently than light of long wavelengths, then we've got a dispersal of wavelengths over here on this side, and just a narrow band of wavelengths is getting through our exit slit. Then our wavelength can be selected by turning our prism here, and then as we turn the prism, we'll shift which wavelength of light is passing through our exit slit. So our monochromator is then selecting monochromatic light from polychromatic light. Note here that monochromatic is one wavelength or a narrow band. This is literally one color. Mono, one, chromatic is color. So polychromatic then is many colors or many wavelengths of light. This is wideband light. So the monochromator is taking in polychromatic light and emitting monochromatic light. And by emitting, what I really mean is it's taking all of the wavelengths that we don't want and it's removing them. It's not changing them into that single wavelength of light that we want. It's just filtering out all the ones that we don't want. Now, modern monochromators don't use prisms, as in our simple example. They use gratings or diffraction gratings. So a grating or a diffraction grating is a reflective or transmissive surface with a series of closely spaced lines. So we have a bunch of surfaces like this at some angles. We could also do this with a series of lines and we could allow the light to move through. But hereafter I'm going to discuss gratings assuming a reflective surface. Similar statements can apply to transmissive gratings as well, but I'm going to largely ignore those. So, when light is reflected from a grating, each line is acting as a separate light source. So, we've got some light coming in. Some of that light is going to bounce off of this surface, but some of that light is going to bounce off of that surface. And now we have two different sources of light passing our light this way. Now, light emitted from multiple sources can undergo diffraction. That is, the reflected light rays will constructively and destructively interfere depending on whether they're in phase or out of phase. If they're in phase, then they constructively interfere. If they're out of phase, then they destructively interfere. If they're somewhere in between, then they partially destructively interfere. So again, the light rays exhibit fully constructive interference if the path lengths differ by an integer multiple of the wavelength. The light rays will exhibit fully destructive interference if the path lengths differ by a half integer multiple of the wavelength. And if the difference between our path length is something other than a full integer or half integer, then we'll get partial cancellation. So the path lengths here differ by the quantity A minus B in our figure. So we've got our light coming in either here or there. As we have this light bounce off of that grating surface and come up this way, and this light bounces off of this grating surface and moves up that way. We can do some geometry, and we find that if we draw 90-degree angles here with respect to this ray and that ray, we draw them this way and that way, then we've got a line segment here B and a line segment there A. If those line segments are the same in magnitude, then our light coming off of our surface will be exactly in phase because those rays have traveled exactly the same distance. But if the magnitude of A and the magnitude of B are not exactly the same, then those two light rays have traveled different distances and now they're not necessarily in phase anymore. They may be in phase if that difference is a full integer of the wavelength of light. So constructive interference then occurs if n times lambda is equal to the absolute value of A minus B, where n is 1, 2, 3, and so on, any natural number. N equals 1 is our first order diffraction, n equals 2 is our second order diffraction, and so on. Our incident angle theta here is defined to be positive, and that means that the diffraction angle phi is negative. The distance between our grooves This is parallel to the bulk surface, not parallel to the surface of each groove, is d, and this is what we call the grating spacing. So we can now calculate the values of a and b. We know that a is equal to d sine theta, and b is equal to minus d sine phi. And now we can determine then the wavelengths that undergo nth order diffraction. So n lambda is equal to d times the quantity sine of theta plus sine phi. And note that for any theta phi pair, there's more than one wavelength diffracted, because we can have n equal 1, n equal 2, n equal 3, and so on. But the intensity of the nth order light is less than the n minus 1th order light, and that means that light beyond our second or third order is negligible. So here we have a rough schematic of a Czerny-Turner grating monochromator. We have our light coming in through our entrance slit. It's being collimated by our collimating mirror over here. It then hits our grating. That light is dispersed. And so you note that up until this point we have white light coming in, and now we no longer have white light. Now we have red, green, and blue light. Then it hits our focusing mirror, and only one wavelength, in this case it happens to be the green, goes through our exit slit and on through our sample and then to our detector. Now, if we want to change which wavelength of light comes out, we can rotate our grating, and if we rotate the grating one way, then we'll shift the blue light to go through our exit slit, and our green and red will come off on this side. Or we could rotate the grating the other way, and our red light will go through, and our green and blue will come off on this side and not pass through our exit slit. So now let's talk about the performance of some grating monochromators. The resolution is the ability to separate two closely spaced peaks. The higher the resolution, the smaller the wavelength difference, our delta lambda here, that can be distinguished. And we measure this as the value between two peaks is 3/4 of the height of the peaks. Now, the resolution of a grating is given by this equation. So we have our wavelength lambda divided by our resolution, delta lambda, is equal to n. N is the diffraction order, times capital N. Capital N is the number of grooves that are illuminated on our grating. The dispersion is the ability to separate wavelengths differing by delta lambda by a difference in angle, delta phi, in radians. And dispersion is given by this equation. So we have our difference in angle divided by our difference in wavelength is equal to n divided by d cosine phi. For example, a grating with 1,000 grooves per centimeter gives a dispersion of 5.8 degrees per micron at first order and at phi of 10 degrees. And in order to select a narrower band of wavelengths from our monochromator, we can then decrease the width of the exit slit. But this decreases the energy reaching our detector, and this means that the resolution of our closely spaced peaks is attained only at the expense of signal-to-noise ratio. We're going to abbreviate signal-to-noise ratio as S/N, both capitalized. Now, the efficiency of a grating is defined like this, where we have this term on the top, this E lambda grating N, is our irradiance at a particular wavelength that's diffracted at order N, and this term in the bottom here is the irradiance at the same wavelength that would be reflected by a mirror of the same material. So the efficiency is how much light is coming off of our grating at that wavelength, at that order, divided by how much light would come off of a plane mirror. So the blaze angle influences the efficiency. The blaze angle here is the angle of each individual surface on our grating compared to the bulk surface. And the reflection from a surface is maximum when the incident angle alpha equals the angle of reflection beta. And note here that alpha and beta are measured from the facet normal, not the bulk normal. If we want to maximize diffraction at a wavelength, then we choose the blaze angle that satisfies both of these two equations. Each grating is optimized then for a limited wavelength band, and a spectrophotometer may thus need more than one grating in order to scan through its entire spectral range. So let's talk about choosing the monochromator bandwidth. The wider the exit slit of our monochromator, the wider the band of wavelengths that pass, and the lower our resolution is. But the larger our signal will become. We generally measure our slit width in terms of the range of the wavelength band passed. That is, instead of saying the slit width is 0.3 millimeters wide. We instead say that the bandwidth getting through the slit is 1.0 nanometers wide. Now, narrowing the slit width reduces the signal-to-noise ratio, so we must strike a balance between the signal-to-noise ratio and our resolution. And generally, the monochromator bandwidth, that is 1/5 of our peak width, provides a reasonably small distortion of our peak shape. So if you look over here, you can see that if we have a wide monochromator bandwidth, we're allowing through, say, 2.0 nanometers. We've got some peaks here. This just looks like a single peak. But as we decrease our monochromator bandwidth, we can start to see that no, there are in fact 2 peaks there. And if we decrease even more, we get to see now there's a shoulder on 1 peak. So maybe there are in fact 3 peaks there. And let's decrease again, and now we can see, yes, there's 1 peak here, there's another really tiny peak there, and there's another slightly smaller peak here. And if we go down to 0.1 nanometers, now we can really easily see in this blue spectrum that we have in fact 3 peaks there. So straight light is unwanted light. This is wavelengths outside the band, not band, expected from our monochromator, and there is always some straight light in our instrument. We can't ever get rid of all of our straight light. So straight light from our source may pass the monochromator from diffraction at undesired orders or angles and scattering from optical components, so mirrors or gratings, and any walls. Usually we paint the walls black so that we minimize any scattering or reflection off of our walls of our instrument. But straight light may also originate outside the spectrometer if the sample compartment is not fully sealed. So you need to be really careful that you've sealed or fully closed the sample compartment. If you have any tubes going into the sample compartment, you want as much of the light blocked around those tubes as possible. Now, naturally, straight light is of greater concern at high absorbance because very little light is getting through our sample, and straight light is then a larger fraction of the light that's striking our detector. And straight light is expressed as a percentage of P naught, the radiance striking the detector in the absence of our sample. And straight light in research quality instruments can be 0.01% to 0.0001%. Now, we often remove or filter bands of radiation using a filter. For example, our diffraction grating selects light of wavelength lambda at first order, but it also passes second order light at lambda over 2. Now we can use a filter to remove this stray light. And that was monochromators.